I'm on page 78. I'm not going to write all these properties down, but let's go through them in that little box towards the bottom where it says real number properties. Actually, we need to talk about the real numbers.
Where's
We
Linda?
did.
I brought her $1.
We didn't do this.
Wow.
The one time you actually grew.
We didn't do this at the beginning of the year, did we? Natural numbers and all that stuff.
Natural's like 1, 2, 3, right?
Yeah, sometimes they're called counting numbers. 1, 2, 3, 4.
Someone put all my paper.
Whole numbers.
A kid got my binder ripped out all my paper.
Yeah.
1 and a third.
Are you being serious?
Okay.
Yeah.
Whole numbers are any number that you can find in nature, right? So it's including 0.
Any number you can do what?
You can find in nature, including
nature.
0. That's how I would do it.
Huh. Never heard that. Yeah, whole numbers include 0. Integers.
Like you can have.
Look, guys, a 3. Integers.
Must have ripped out my paper.
That does include negative numbers.
So yeah, it's like all the numbers you normally see on a number line. This is where it gets messy. Rational numbers.
1/2.
Okay, yeah, this one's messy. Anything that can be written as a over b, where a and b are integers. So, yes, it can be 1/2, -9, 4s. How about 7? Is that a rational number?
7/1.
7/1. So yeah, 7 is rational. Let's see. How about 0.5?
Yeah.
Because that's the same as a half. How about 0.3 repeating?
No. 1/3.
0.3 repeating is 1/3. All repeating decimals are fractions also. Yeah.
Oh,
But if it's an infinitesimal that does not repeat,
like pi.
like pi, it's called irrational. Like pi, or square root of 3, or 0.2178914 assuming it never repeats. Those are irrational. So these are like the weird ones. Do you guys remember how this works? So notice that all the natural numbers are also whole numbers. So you could say natural is a subset of whole numbers. All the whole numbers are integers. So whole numbers are a subset of integers. And all the integers, because of this rule, anything over 1 is equal to this. Because you could write all these as fractions if you just put them over 1. Basically, they're all rational too. So it's the Russian nesting doll thing. All naturals are whole numbers, all whole numbers are integers, all integers are rationals. So everything up here is a rational number. And everything that doesn't fit up here, we throw in the bucket down here in irrational. All these numbers together, every number you ever seen together is called real. Okay, so if it says real numbers, it means everything, basically. There is something called imaginary, but we're not doing that.
What is imaginary?
No, he's exaggerating. All right, 78. It's not bad. So okay, you guys see that little box down there? The orange box, nice pretty orange box. So these are properties of real numbers. We're gonna have to. These will be like the answers to some of the questions today. So the first thing is called the identity property of addition. And then on the right side is the identity property of multiplication. So what is the identity property of addition? Can you guys put it in your own words? Yeah,
Any number plus 0 is that.
right. Any number plus 0 is equal to itself. What's the identity property of multiplication? Same thing. Any number times 1 is equal to itself. Inverse property of addition. When you add negatives, add opposites,
Cancels out.
they equal 0. The multiplication property is a little bit different. When you add, what's that called when you flip it upside down? Reciprocals, yeah. When you multiply reciprocals, what do they multiply to? 1. Commutative property. We never discussed this in algebra because you don't really need it to do algebra, but you guys know these are true, right? A plus B, same thing as B plus A. Commutative property of addition. Commutative property of multiplication, A times B equals B times A. So order of addition doesn't really matter, order of multiplication doesn't really matter, that kind of idea. Associative property, if you add the first two things first, if you're adding three things and you add the first two first, or the last two first, it doesn't matter, they're still equal. You guys see what it's saying there? Associative property of addition, they put the parentheses on the first two first and then the last two, and they're still equal. Basically, it's another order of addition doesn't matter thing. Does order of multiplication matter either? No. Associative property of multiplication, A times B first, is the same thing as doing B times C first. You get the same answer. Distributive property, that's the property we actually did talk about a lot because we used it a lot. You guys remember distributive property, I assume?
Yep.
A times parentheses B plus C. Here, I'll change the letters so we have to think about it a little bit. What would this equal?
X
X
plus
plus.
X.
So yeah, distributive
Oh,
property.
that's a Z? How come it's a 2?
Okay, and then on the top of page 79, a bunch of little sillies. The ones on the top of page 79, yeah, anyway, reflexive property. Something is equal to itself. Mind-blowing, right? Symmetric property, if A equals B, then B equals A. Transitive property. This one we kind of already talked about. If A equals B and B equals C, then what?
A equals C.
A equals C. So on the logic chapters that we did, this was called the law of transitivity, but now it's called the transitive property. If this is the same as this is the same as this, and A and C are the same. It's like a train, remember it hooks together like all the carts. Was that Friday or was that Thursday? We talked about this one.
I think it's Thursday.
Probably Thursday. Were you guys here for that?
I don't know.
Transitivity?
I don't think we were.
Expect
I don't think
train.
so.
No, I think that was Friday.
Yeah,
I think it was Friday. Okay. So when we're solving algebra problems like x plus 3 equals 7, how do we solve that algebraically?
Plus, -3.
Minus 3. Okay. When we do that, when we like do the same thing to both sides and we get another equation down there, that's called the property, the addition property of equality. Now, why is it called the addition property if we subtracted?
Because you're adding them.
Because when you subtract 3, that's the same thing as adding -3. So instead of calling it the subtraction property or the addition property, they just always use the addition property. Okay, of equality, because it's basically saying you can add the same value to both sides of an equation. You can add the same values to both sides of an equation. And similarly, if we had like 3x equals 12, we divide by 3, guess what this is called?
Multiplication property.
Yeah. Because dividing by 3 is the same thing as multiplying by reciprocal, 1/3. So they call this the multiplication property of the polygon. So if you add or multiply or divide both sides by the same number, multiplication property of equality. Now I didn't name these properties when we learned this stuff, because you don't need to know what it's called for it to work. Okay, the next one is very important because we're going to use it a lot in geometry when we get to the geometry stuff. And we've used it some in algebra too, but substitution. Basically, we did an entire chapter on that last year. When we're solving two equations together, we use substitution a lot. I'll give you an example, like 2x plus 3y equals 10, and y equals 2x minus 1. So we can solve these equations together. Like there's one solution, like maybe it's 3, 2 or something. One solution that's going to work in both of these equations. It's not 3, 2. But one way we could solve it is substituting. Y equals 2x minus 1, and we put that in for the y in the other equation. You guys remember doing that last year?
Oh, yeah.
Yeah.
So substitution just means replace something with something else we know it's equal to. And yeah, I'm
I
not
remember
going
especially hating substitution.
to. Did you?
I remember liking it. Over the other one, there was the.
Yeah, the other one was way better.
Elimination.
Yeah, that one was way easier.
Okay.
Oh, wait, was it? Maybe I did.
Okay.
Too far.
Trichotomy property. You guys see where it says that? Anybody try and tell me that in their own words? Not Abby.
I'll read it to you.
No thanks, Leah. Do you understand what it's saying?
Yes, what
I
you
just
just
don't know how
can't
to put
explain.
that in my words.
Yes, you can.
I will,
Explain
I
it.
will then.
Okay, go.
For any two numbers.
No.
When you have any two numbers,
Okay.
one will
Numbers.
always be exactly equal, greater, or less.
Yeah, basically. They have to be either the same or the first one's smaller or the first one's bigger. That's okay. Yeah, it's not trying to trick you or anything. It's just a lot of these properties are does statements. Properties are kind of basically their postulates. You remember what postulates were? Like rules that you can't prove, you just assume are true, and they're pretty basic ideas. So yeah, all these algebra properties are basically postulates. Okay. So we're getting ready to do proofs. There's a definition of proof at the bottom. Is a system of reasoning or argument to convince a person of the truth of a statement. Truths are deductive reasoning. Remember, you guys weren't here. Deductive reasoning is given these set of facts, assuming these are facts, then I can step by step argue that this must happen. That's kind of what we're warming up. So we're warming up to a geometry proof using algebra, because you guys are a little more familiar with algebra than geometry. So that's the goal for today. Okay, we're on page 80. I think I'll do... Oh, you know what I didn't do?
What did you not do?
I didn't put the letter symbols for each of these. I didn't leave myself any room. Guess what letter represents natural numbers?
A, B,
And
X.
N. Where are you guys getting these letters from?
where'd you get X?
Right.
X.
It's common.
Okay, guess what represents whole numbers?
A W.
Guess,
Why should be like
guess what represents integers?
An I.
C.
Okay,
Correct.
did you really guess Z?
I just didn't. What the heck?
I thought you were looking in the book.
No.
Why
Okay,
does Trey have to be right?
talk to God. So yeah, Z. I don't know why they chose Z. I know why they didn't choose I, because we use it to represent something else, imaginary numbers. Okay, R,
Is that
irrational.
R?
Okay,
Q.
What?
they use Q. The reason they didn't use R is because they use that for real numbers.
I got it.
Now, and all these letters are actually supposed to be a little like fancy, like have double lines or something, but I'm not gonna worry about that.
No one cares about that.
And then irrational basically means not rational, so what they did was they
within
put a Q with the not symbol. Remember that?
Apostrophe.
Apostrophe meant not on the logic stuff we did. So,
So not.
yeah, they probably wrote that in the book somewhere, did they? Yeah, kind of. They did. It's kind of scattered out through the first few paragraphs. Okay, so you don't have to write. I guess if you didn't remember the letters, you could just write the word out, right? You don't have to do that. So, number 1 and 2 are a little bit different. Number 1, we're supposed to say all the sets that the number could go in, and on number 2, you're supposed to say the most specific set that the number can go in. So, on the most specific set, basically you want to go as high up as you can. This is the smaller set. Even though natural numbers, the set of natural numbers is infinite, because this goes forever. But it's still a subset of this set, or this set, or this set. So, the most specific sets are at the top. Like, if you get the number, let's say 3. Is 3 a natural number? Yes. Is it a whole number? Yes. Is it an integer? Yes. Is it a rational? Yes. But the most specific set is at the top, so you can put natural numbers for that. This is number. That's for number 2, actually. And number 1, we're supposed to list all the sets. No, wait. I might have said that wrong. State all the proper subsets of. No, I said it right. Number 1 is use all the sets that they would fit in. So number 1, A is 1/2. So what sets can fractions fit in?
Rational.
Rational. And that's it.
Oh.
So just put Q for that one. On B, what sets can 7 fit in? Or 7 over 1?
Rational.
Rational, full, and natural.
Okay, all the above, right? 7 would be in all these. It doesn't matter that they wrote it as 7 over 1. It's still worth 7.
How is
Just
it
put
in?
all the above.
How is it
No, it doesn't go in irrational, but just write those 4. How's it in what?
in integers?
Integers are all these numbers. So 7's gonna fit in that. Okay. On square roots, if I did like square root of 9, where should that go? If I did like square root of 9.
Irrational.
No.
Rational.
Square root of
Oh yeah,
9
because it turns into a 3.
Yes.
is a 3, so it goes in all these.
Yeah. Oh.
But if most square roots don't simplify completely like that, so most square roots are irrational. But if it is a normal number like 3, then just think of it as a 3. It goes in all those. Okay. So on number 1, you should have multiple answers on pretty much all those, almost all of them. Number 2, A, where does pi go?
Irrational.
Irrational. What's the symbol for that?
Q with the little.
I think the way you say it, I want to say the way you say that is Q prime. But basically not Q, just
It's a total
put Q with the
quantity.
apostrophe on there.
It's just a weird cube.
Okay, on V,
So rational.
repeating decimals are basically fractions. So it's rational. So, sorry, on number 2, you're supposed to be as specific as you can.
Oh.
So now fractions only fit in rationals. Pi only fits in irrationals. But like I said, if we have the number 4 or whatever, that would go all the way up here to natural numbers. Even though it fits in all these, you would go up here to the natural numbers. That's more specific set.
Okay.
So there should only be one answer on number 2 for each of those. Okay, now I'm jumping to number 3. Yeah, I'm jumping around a lot. Number 3, you guys should recognize that right off the bat.
That's algebra.
Yeah, what's the property called?
Distributive.
Distributive property, and that's what we're supposed to write. Also.
Just that? No math?
Distributive property. No, we're not solving anything.
Good.
I like algebra better now.
Okay, if x equals 6 and 6 equals y, then x equals y. I'm on number 5, if you can't tell.
That would be Trichotomy.
You need some work on phonics. Transitive property. Okay, so for 7, you just have to go back and look in the box. I'm not going to have you guys memorize these, by the way. I'll tell you, but before we get to the test, I'll tell you what you need to have memorized, and it is not the algebra properties.
When's the test? Like next week?
Not, yeah, maybe next Friday or something.
Okay.
It's kind of a big chapter-ish. Anybody find number 7?
Yeah.
If you look on page 78, it's towards the bottom of that box. Do you guys see it?
That's associative.
Associative, you gotta be a little more specific. Associative property of addition. So there's a multiple. Huh? No, associative property. So commutative is would be 3 plus 9 equals 9 plus 3. Associative is when you're adding like 3 different things and you add the first 2 first and the last 2 first.
Associative is when you're like
Yeah. Anyway, you don't have to have these memorized. You can just kind of copy it down from it. So there's an associative property of addition and there's one of multiplication. So if they're multiplying in the problem, just write associative property of multiplication. Okay, number 9. 3a equals 9, then a equals 3. How did they figure that out?
Common sense.
Divide by 3.
They divided by 3. What was that property called? We talked about it earlier. See where I put it. Divide by 3.
Multiplication property of equality.
Yeah, basically they're multiplying both sides by 1/3. So it's a multiplication property. If they divide or multiply both sides by the same value, it's multiplication property of equality. If they add or subtract the same sides to an equation, it's addition property of equality. Okay, this next part might be a little bit weird. So we're jumping to 20. You see that there?
Wait, oh yeah.
Okay, it says in 20 through 24, write a statement representing the relationship. So we're supposed to do the reflexive property, but we're using less than or equal to. So if you turn back in your books to top of page 79, the reflexive property is A equals A. So what do you think it would look like if I use the less than or equal to symbol?
A is equal to or less than
A is less than or equal to A.
Do we just write that?
Yeah. So that's what.
There's nothing
if A is equal to A, which obviously it is, it's also less than or equal to A, right? So that's still reflexive property. Transitive property for greater than. So remember the transitive property was A equals B, B equals C, then A equals C. So what would that look like with greater than symbols?
A is greater than B, and B is greater than C, then A is greater than C.
Yeah, does that make sense? If A is greater than B, and B is greater than C, then A has to be bigger than C. It's kind of like if Bob is bigger than Bill, and Bill is bigger than Tom, then Bob is bigger than Tom.
Tom's pretty short.
They're both bigger.
Yeah. Okay. 22, these are kind of tricky, so I'm just going to step through them. Symmetric property of perpendicular lines. So if you look at symmetric property, it's towards the top of 79. It says if A equals B, then B equals A. So how can we do that with perpendicular lines? Have we talked about the perpendicular symbol?
I feel like
I might have mentioned it like once. We haven't really done perpendicular lines yet though, like maybe one day. I don't think we've really covered it though. That's the perpendicular symbol. Do you guys remember what perpendicular means?
Go
they cross it, right?
right.
They make 90-degree angles. So are these lines perpendicular?
No.
No, they're intersecting. So I'm going to say AB is perpendicular to CB. And then
CD would be perpendicular.
CD is perpendicular to AB. It's kind of a duh statement. I would probably never use this property in a proof because it's too
Simple.
it's too basic. Just a little too
E.
It's a little too duh. Okay, actually 23 and 24 are pretty much the same thing. You guys remember the parallel, did we talk about parallel line symbol?
Yeah.
It's a
Yes.
two.
Yeah,
Two lines.
we did do that one. So yeah, it's double lines, so it's pretty much the same.
So AB is parallel to CD, and CD is parallel.
Go ahead and try 24. After you've done 23. All right, on 25, if you have questions on those, you can ask later. On 25, explain why there is no reflexive property for parallel lines. So the reflexive property flip back says A equals A. So why does that not work for parallel lines? Why can't you?
Would it be the same line?
Yeah, can line AB be parallel to line AB? No, can't. A line can't be parallel to itself. This one's a little trickier. Explain why there is no transitive property for perpendicular lines. You guys remember transitive?
A.
So let's write out as if it did work. So the book kind of cheated and used one letter for these lines, but it's okay. So if AB was perpendicular to CD and CD is perpendicular to EF, I guess, then AB would have to be perpendicular to EF. So if it did work, it would look like this. Now let's look at the picture. Now let's say this is AB, and let's say this is CD, and then EF is supposed to be perpendicular to that.
They would be
That's what this says.
parallel.
Yeah. So basically, what happens when two lines are perpendicular to the same line? They're actually parallel. They're not perpendicular at all. They never even touch. So just say that. When two lines are perpendicular to the same line, then they are parallel. That's actually a theorem. We haven't really proven it, but we'll just go ahead and say it. All right, jumping to 33. Okay, these are proofs. So let's start off here. Okay, so what they're doing on 33 is they wrote half the proof for us, and we're supposed to fill in the blanks. So here's normally what a proof looks like. There's two columns, and then there's a bunch of statements, like statement 1, statement 2, statement 3. So after each statement, you give a reason that you can say the statement is true.
Proof.
This is a proof. This is what a
Yeah,
proof
yeah.
looks like. So this is like a formal argument where you're going to start by saying, this is true, and this is why I know it. Then this is true, and this is why I know that. And this is true. And you keep going as long as it takes to get to the point you're trying to prove. Okay, the first line is basically always the same thing. You have to start with your basic assumptions. Like on number 33, they're saying, if you read 33 at the top, it says, if 90 equals 3x plus 3 times x plus 13, then x equals 17. So we're assuming that 90 equals 3 times x plus 13. And how do I know that's true? Because they told us. Okay, that's our starting assumption. So basically, every first step on a proof is just starting with what is given to you. So the reason is always just going to be given. You kind of repeat what they tell you the starting point is. This is our starting point. It was given to us. And then we could probably do this without looking at the book. But if you were solving this on your own right here, what would be your next step? Distributive property, right? So see what they put down there? 9 equals 3x plus 39. I'm not going to make you copy that down because this one is full blank. But yeah, what's the reason we know that? Distributive property. I don't know how you prove the distributive property. I guess you can't. All right. Number 3. Okay, well, peek back up here. What would be your next step if you were solving this?
Subtract 39.
Okay, yeah, they didn't show that in the problem. All they showed was, what is it, 51? All they showed was that. So, but what did they do to get that? They subtracted 39, right? So what's that called when you subtract the same value on both sides?
Addition property of equality.
Addition property of equality. Good. You only need to be told twice.
So it's a proof, pretty much a play-by-play of doing an algebraic problem.
Well, this is like the only assignment where we're going to do algebra proofs.
Okay.
We're more familiar with algebra, so this is kind of like a warm-up for us. And then if you guys were doing this, what would your next step be?
Divide by 3.
Divide by 3. So that would make that like 17 equals x.
Multiplication property of...
I'm not even sure which line they left blank here, but I'm just writing it all down. Multiplication. Multiplication. Property. I'm going to start abbreviating for this. Okay, and that's what we were trying to prove, right? Remember at the beginning it said if blah blah blah, then x equals 17. So,
What about...
oh yeah, they switched it. So, I said earlier I would never use that property, but they did, the book does, so let's go ahead and do it. If 17 equals x and x equals 17, what is that called?
Symmetric property. So it's pretty much symmetric property, just switching it around.
Yeah,
Why?
I think they're taking nothing for granted, I guess. Yeah, so if I was writing my own proof, I would not do that.
Seems kind of useless.
I'm not quite that nitpicky.
Yep.
Okay, I'm gonna leave. No.
Algebraic proof of each step.
Gosh. On 34, they had to throw us a curveball. I wish they would have done one more,
Like the last one.
like the last one. Well, on 34, you guys see what's different about that one?
Well, not all the blanks are filled in the last, and there's only 4 steps. Definition.
Well, it's the absolute value part.
You should just work on the ones that
So,
starting with.
on the second to last, I'm not gonna do this with you. On the second to last line, it has that. If absolute value of x equals 4, then what do we know?
Then it equals 4.
No?
X equals 4.
It could equal 4, or it could equal
Or
negative 4.
Negative 4, right? And how do we know that's true?
The lines.
Because that's what absolute value means.
Yeah.
So it's the definition of absolute value.
Uh,
Okay, they wrote in definition of absolute value. So we just gotta write that thing. Also, we know that the last line has to end with what we were trying to prove. And they see up top it says then x equals negative 4 or 4. It has to end like that. That's when you get to that point, you're done with the proof.
35 is like number 33, except you write everything down.
Yeah, 35 is like 33 and 34 combined, but you have to do it all on your own.
Great. Okay. Cool.
No. Trouble.